Hello students, welcome to one more video on linear integrated circuits. In this video we shall see application of triple timer, which is Astable multivator, an advanced application. Let us proceed and try to see what is this application. Because a recap of what's the Astable multivator. Astable multivator does not have a stable state. Output level will be keep switching from low to high and high to low continuously for a specified duration. Duration of low and high levels are predefined. That is, on time and off time is predefined using the values of resistors which are connected external to triple timer. This is a circuit diagram and the corresponding waveform. So we have a triple timer and we have two resistors RA, RB and C. So as we know in the previous videos of a stable multivator, RA and RB is the resistors which will assist the capacitor to charge to VCC towards VCC, and the capacitor will discharge to ground through RB and the transistor Q1. So this way the capacitor charges and discharges so that we get a square wave of specified duration. So the values of RA, RB and C will decide what is the period and what is the on time and off time of the square wave. The amplitude of the square wave is high voltage is VCC, the low is 0 volt. Now we also seen the expression for the on time and off time. So on time expression is given by 0.69 C into RA plus RB, whereas the off time expression is given by 0.69 C into RB. The total time, so TH plus TL is given by just the addition of two times. One thing we can observe in this particular circuit, as you can see here. So while charging, we have this RA and RB are associated. While discharging, only RB is associated. Meaning, even when the values of RA and RBs are same, it is not possible to get a duty cycle less than 50%. So even if RB is very small, so the duty cycle given by TH by total T. So we want to always have the duty cycle more than 50%. So using this circuit, that is using this basic circuit, it is highly impossible to get a duty cycle less than 50%. So we need to modify this circuit so that we can get a duty cycle less than 50% also. But using this circuit, we can get any duty cycle which is more than 50%. We can get a duty cycle of 70%, 80%, 95%, 99%, anything you can think of. But it is not possible to get a duty cycle less than 50%. So this circuit has to be modified so that we can get a duty cycle of desired value even less than 50%. Let us have a look at this circuit here. So the modification from the first to second circuit is, here you can see there is a diode existing across the resistor RB. Now it is necessary to observe the charging path for this capacitor is now changed, because when you have two paths for a capacitor to charge, now capacitor can charge through RA and RB, and it can charge through RA and this diode. So during the charging condition, this diode will be on. So once diode is on, its resistance is very small. The capacitance will certainly choose a path of lower resistance between RB and the diode. It will certainly choose the diode, meaning the on the path for the capacitor during charging is it charges to VCC through RA and the diode. So now the time constant becomes RA into C only, neglecting the on resistance of the diode. As you can see now, the expression for T on becomes 0.69 Ra into C. Rb is not coming to picture because Rb will not be uh, uh, assisting the transistor, the capacitor charge. Now capacitor charges through the diode. So even though diode has got a very small resistance, it will certainly be far less than Rb. So that current chooses the path through the diode while charging. So that's why this T on expression doesn't have an Rb term in this time expression. To be very frank, this resistance would have been Ra plus Rf, which is Rf stands for the on resistance of the diode. So since that on resistance is very small, so that what is this Rd on is very small compared to Rb. We are not writing it there, and you can see. So when the capacitor is discharging, it again has two paths towards ground. You can see it can go through Rb or it can go through the diode. If it wants to go through the diode will be get reverse biased because you are trying to push a current from N type to P type. So it will get reverse biased. When it is reverse biased, its resistance is very high. So that's why while discharging, the capacitor current will certainly choose RB path, a lower resistance path while discharging. So that there is no change in the expression for the off time. As you can see now, since T on depends on only Ra and T off depends on only Rb, the duty cycle you can get any amount of duty cycle, even you can get a duty cycle of 10%. How do you get a duty cycle of 10%? Make this Ra smaller compared to Rb, so then the on time is less than the off time. So on time is less than the total time T, so naturally the duty cycle becomes very less. So by changing the values of Ra and Rp using this diode, you can able to get duty cycle of any duration, even from 10% to 90%. So how do we get 90% duty cycle? Make this Ra very large compared to Rb, so that you get the duty cycle large. If Ra is very small, you get a duty cycle less than 50%. Suppose in the next circuit we shall see if I reverse this diode what happens. That's what is the next circuit. Suppose if I reverse this diode, you can see what's happening. So can you think of what is the effect of making this diode reverse? So since the diode is reversed, now while charging the capacitor path is Ra and Rb, while discharging its path is through the diode. So you can see when it is charging, it is Ra plus Rb into C, the time constant. When discharging, it does not pass through Rb, it will pass through the discharge current will pass through this diode. So that's why it is this. This is no more Rb, it is now Rd on. So since Rd on is very small, the total time will be almost close to T on. So this duty cycle of this particular circuit will be very large compared to 50%, maybe around 85% or 90%, depending on the value of Ra. So if Ra is in terms of tens of K, so we're going to get duty cycle maybe close to around 95%. The value of Ra is around 1 of K, now it may be around 80% or 75%. So that we can see it in the simulations. We shall have a look at some of the simulations of this LT spice and then try to understand in a better way. You can see now we have a military circuit after we got memory a stable version. Now you can see there are two resistors R1 and R2 which are forming Ra and Rb. So there is a capacitor C1 which is a timing capacitor, and there is one more capacitor C2 connected to this CV, that is control voltage. Control voltage is nothing but VTH. VTH, in order to keep the VTH at 2/3 of VCC, we are having a capacitor of 1 microfarad. So it is used as a voltage stabilizing capacitor. And we have this trigger and the threshold connected to shorted and connected to this junction of the capacitor, and this is your discharge pin, which is VCC. This is grounded here. There is a final output, and reset is again connected to VCC so that it is made deactivated. Suppose we know that if the reset is made 0, the output becomes 0. So it resets the output. Now we have R1 is equal to R2 and we have a capacitor of 0.1 microfarad. So let us see now we are supposed to get a duty cycle which is more than 50%. Now since on time is more than off time, so let us see how do we get the. So this is can also see this capacitor voltage, capacitor charging, discharging. So let me have one more pin and then try to have. You can see the capacitor is charging from 1/3 VCC to 2/3 VCC. Let me just have a cursor. So let me take this cursor and try to see what is this voltage is. So 1/3 VCC, 1/3 of 5 is 1.66 and 2/3 of 5 is 3.33. You can see the capacitor voltage is ranging from 1.66, that is 1/3 VCC, to 3.33, which is 2/3 VCC. If the capacitor voltage tries to go below 1/3 VCC, output goes to high. If the capacitor voltage tries to go above 2/3 VCC, output go to low. So this is keep on happening. So whenever this goes to below 1/3 VCC, the output goes high, the capacitor or the transistor turns off, capacitor starts charging. If it tries to go above VTH, the transistor turns on, so capacitor start discharging. So that's what it is. Discharging is keep happening without any hurdle. So that's why this is called as a stable multivibrator. Now let us try to put a diode to this circuit and see how does the circuit changes. Now let me put a diode here. So this is a diode. So let me just have the diode and place it across RB. I'm just placing the diode such that it bypasses the resistor R2 when it is charging. Now we are having a diode now connecting across R2. Now let me save this and run the simulation. Now you can see earlier the duty cycle was around 70-80%. Now the duty cycle is almost 50%. Now you can see on time is almost equal to off time, because on time is now 0.69 RA into C and off time is 0.69 RB into C. So since RA and RB are same, we are getting duty cycle almost 50%. Now let me make this resistance of RA, that is R1, bit smaller, maybe 1K. Now the on time is maybe 10% of the off time. So let me run this now. Now you can see it is on for a smaller duration and it is off for a larger duration. You can see the on time is less and the off time is more. Now this was not possible without the diode. So the on time is less, off time is more. So if I do the vice versa, suppose I make this 10K and I'll make this 1K. I can make the duty cycle around 90%. Now you can see it's the reverse. Now the on time is more, now, the off time is very less. So we can able to get any duty cycle starting from 2%, 5% to 95% or 98% by having that diode. So let me just reverse the diode and try to see what happens. So let me just reverse this diode. Reverse the diode. Naturally, the off time should be very small now. So let me run this. If I run it now, you can see the off time is very small. So let me just delete this. Okay, I can see the on time is, this is capacitor taking longer time to charge. The off time is very small. because half time is through the diode.